Okay, so it's a great pleasure for me to welcome Professor Nael Abu-Ghazaleh. I hope I got the name pronunciation right. He's a professor in computer science and ECE at the University of California, Riverside. His research is in architecture and system security, and he's been I first saw him recently at a workshop that Google organized, and he had words like security and privacy and heterogeneous architectures and AR, VR, and sensors and cameras in his talk. And so I said, well, we got to get him here and get him involved with this project. So yeah, without further ado, let me welcome Nael, and we look forward to your presentation. And this is informal, so we can feel free, like everyone knows, feel free to ask questions. And the goal here is to learn about your work, but also see how we can integrate some of this in ILLIXR, have ILLIXR help your project, and push the field forward together.
Okay, great. Thank you very much for the introduction, Sarita. So this work is with Professor Jiaxi Chen, who's here. Carter and Yicheng are the PhD students that are doing the heavy lifting on the work. Carter is in his final year. He's on the job market if anybody's looking for a great AR, VR security expert to hire. And Yicheng is here as well. He's in his second year of the PhD. So I guess I'm preaching to the choir. So I'm not going to spend too much time motivating that AR, VR is the next frontier in computing and living. And you can think of this as a progression. You can start at any time in the history of the development of computing. And we have this continuous sort of evolution towards mobility, portability, ubiquitous computing. And now the next frontier is when we are immersing ourselves in the digital world. So you can think about a lot of the applications as we kind of followed this pathway have transitioned to use this next frontier. There's a lot of projection data. This was one of the more conservative ones that I saw, estimating the market to be growing towards $52 billion. This is worldwide market. I've seen others that are an order of magnitude higher than this. It seems clear that this is perhaps past the tipping point and something that we should consider, if not now, in the near future as a mainstream technology. So given something that becomes really popular, it's usually soon after that the attackers follow. And we can think about privacy threats. So as we do more and more in the extended reality space, these activities can be tracked and kind of exposed to the attackers. So perhaps we don't want people to know what we're doing in AR space or VR privacy. Although these seem like novel concepts, it seems like as you spend more of your time in there, this is something that you would like to protect. Of course, in AR context, you are also in the physical world, so this exposes kind of real world privacy, not digital privacy. So as we for example, as the internet became kind of a commercial entity and more businesses shifted to the internet, the attackers sort of appeared. So we moved from kind of early attacks that were denial of service, digital vandalism, to attackers being able to make money on the internet through cyber attacks. So there's fascinating lines of research in the security community trying to break down this. So they evolved into an industry now. It has like a complete supply chain. You have hackers that focus on finding vulnerabilities, and then they pass them off to other people that use them to find machines to attack, to other people that build botnets, and then they monetize the botnet by selling kind of like a cloud system, selling instances where you could run spam or click fraud or whatever your thing is. So as we see that line with the billions of dollars growing, that it's not going to be long until the attackers get there. So this is the right time to think about security and privacy threats. of course, once you start that, then the next question is, okay, what is new? Is this just another basically system where we have to think about cybersecurity? And can we just borrow traditional solutions and deploy them there? Some crypto, some, OS hardening, things like that. I mean, this is only part of it. We have kind of unique threat models, in my opinion. We have the integration of the physical and the digital world in AR, kind of less so in VR, but still some sensor data that gets integrated. We have new application spaces. We have new, basically targets, in my opinion, new threat models and so on. And this is all complicated by the fact that we have to think of this as the systems are being engineered and as they are evolving. So we don't really know what eventually the applications will look like, what the standards would look like, what the protocols, what the systems. So we have to kind of do this on the fly and come up with, maybe sort of ways of building systems that are more secure, so that we end up designing secure systems as we go. Okay, so against this backdrop, I want to tell a little bit of a story about how our group got involved in this line of research. So I guess we were, both Jassy and I were interested in this space independently, and the trigger for us to work together was a call from Meta to submit proposals on privacy and security for AR/VR. So we ended up brainstorming for a while, and we converged on essentially attacks that target location. So to us, it was clear that location is a fundamental kind of value or fundamental property within these systems. You can think about it from the privacy perspective. If you're tracking somebody, then tracking location is something that is really valuable. At the same time, as you are immersed in this world, so again, if you can track location, you could then use it to chain other attacks. You could figure out what you could do next based on their location. So this is the spying part of it, or the tracking part of it. The other part of it is if I can modify the location, and we call these teleportation attacks. If I can change the location either on my headset, or I can manage to get somebody else's headset to change location, then potentially this is valuable to an attacker. So you could think about some private spaces that if I can teleport into, I have access to information, or I can do some things that are not possible for me if I'm outside of this space. So we thought, at least as a starting point, that this is something that is interesting, and we ended up kind of formulating some ideas about attacks and possible defenses within that space. But then once we got started, it seemed like there's a lot more questions than we know how to answer. So we started out with a simpler problem, and a problem that connects with some existing research that we had, which is, given a headset, there are multiple applications that are running on it. This is standard nowadays. You could download apps from app stores and then have them running. And if there is integrated malicious functionality in one of the applications, the application still does not have kind of super user access, but they use their presence on the system to try to infer some information about other applications. This type of attack is called a side channel attack, right? So I observe kind of behavior through measurable values that I can get from the headset. So this is where we started, and this is what I'm going to spend the first part of this talk talking about. Essentially, I'm going to talk about like two different sources of information, and we were able to construct attacks based on both. And we have, so this is work that's currently, we have two papers, both in major revisions that use Next Security 23. So hopefully we'll be able to share something with you soon once they are formally accepted. So the general threat model for these is that within a headset, I am able now to run multiple applications within my field of view. So I could be, I don't know, playing a game, and I have a, Facebook Messenger running, or, having something that tracks weather while I'm, driving or something like that. So you could have these multiple applications integrated running on the same system. They could be visually isolated or they could be overlaid. It doesn't really matter, but they're sharing the same runtime system. They're sharing the same hardware. So they have access to some things, and we'll see that these things will allow us to infer information about the other applications. So this is a somewhat abstracted view of the hardware of a headset, the hardware and the runtime system. I'm sorry, I haven't had time to really dig into ILLIXR, so hopefully this doesn't look too different from what you guys are working on. But essentially, you can think of this as hardware level, sensors. You see the IMU, the cameras, the microphone, some compute, right? CPU, GPU, the holographic processing unit from HoloLens. And then you have some low-level APIs and drivers. And then you have a high-level SDK. So this is things like Unity or Unreal. And then you're developing both services and applications on top of that. And our initial goal in that first paper was these performance counters and APIs that are exposed by these Unity, Unreal, or higher level SDKs. Some of them are passed through to lower level values, and we could have potentially looked at APIs that are directly at here, but it was easy enough to get them from Unity, Unreal. So if you develop an application using these runtime systems, then you have access to these APIs and you don't need to be super user. And there is legitimate need for applications to view these because headsets are highly limited in terms of resources. So I need to be able to get feedback from the system to customize how my application is working. Okay, so this is our goal, the performance counters, or this is our leakage source, the performance counters that are accessible to the user applications. I have to say that there's other types of side channel attacks, micro-architectural side channel attacks that the architecture community works heavily in and my group works in. So those are harder and we think are also present here. So we settled for these easier sources of leakage, but this I think is also another open area for attackers to target. So now here is the overall threat model. So the victim is running, something, maybe interacting with the headset or typing a password or something like that. The spy is running as a background application and trying to sample these performance counters that are accessible. And then as they get this information, they mine it to try to infer some information about the victim application. And these APIs, I'll talk a little bit more about them. So there are memory allocation APIs. So they're not open in the sense that you have direct visibility into the memory usage of the other applications, but it turns out that some memory is shared. So you get like some leakage across them. So there's shared buffer, for example, for some of the sensors and so on. So you can infer some information from, even though you only have visibility to your own memory allocation, there is some shared state that you see. There's rendering performance counters, things like CPU and GPU frame rate. There's device tracking API. So these are more the topic of the second paper that we had. So essentially the sensor information that you have access to. So we started thinking about like what would be of interest to the spy. So what could be the target of the spy? What would they be able to, what are they trying to get? And then we ended up separating these potential goals into 3 different areas. So this user interaction model, the application is trying to infer what a user is doing to interact with the headset. So this is another application spying on you as you interact with the victim application. Another goal is perhaps this is the more conventional use of these attacks on, let's say, Android phone or desktops or so on, is to spy on what other applications are doing computationally. So for example, try to identify what other applications are running on the headset, perhaps to then guide another attack like a phishing attack or something like that. And then finally, we thought about footprints, if you will, side channel footprints that could be a function of what's happening in the environment. So depending on what's going on, so let's say a complex environment might cause a computational footprint that is different than a simple environment. And then we can use that to infer some information as well. to kind of dig down to the next level of that. So, we looked at user interactions involving hands, hand-free, so voice commands and things like that. We looked at detecting applications, so application fingerprinting, and then application monitoring, trying to see what applications are doing at a certain point. And then in the environment, we could try to identify some information about the surrounding space, or even in AR scenarios, for example, the digital artifacts. If there is, for example, a cloud anchor, you might see a different footprint than if there isn't a cloud anchor. But also like spying on what's happening around us, like a bystander might cause, for example, some rendering activity that would not be there if there isn't a bystander. And then finally, this is, I'm sorry, from our paper that's under review, the specific attacks that we ended up implementing, and please ignore the section numbers since they're not relevant for this presentation. So we actually demonstrated end-to-end attacks that were able to derive the hand gestures, to kind of do some keystroke logging, to identify voice input out of limited set of voice commands, to identify and fingerprint an application being launched. And then from the environment, we implemented an attack that does bystander ranging, I should say. So it can detect when a person gets into the field of view, and also the distance of that person, how far away they are.
How is detecting hand gestures a side channel? Can't you just get that directly from the hand tracking data?
So the hand tracking data is not accessible. So it's sort of locked into the application that is using it. So other applications can't directly spy on it. So there's a paper out, I think, HoloLogger, that uses that information to infer, I think, keystrokes. But we found on the headsets that we tested that this is not accessible. So this is one of the ones where it's easy to come up with a permission structure for it. If you are interacting with this application, then you block out.
Then you can. Else. Otherwise, if you're in the background, you do not have access to them.
Exactly. Yeah. For some other sensors, it's trickier to do that. But for this one, it was I think easier and implemented by the headsets that we tried.
Gotcha.
Yeah.
Can I also have a question here?
Sure.
Sorry.
Go ahead, please.
Jay, go ahead. Okay, I'll go ahead first. So you're saying that, for example, like the sensor data from the hand tracking tracker is not that easily accessible. Then can you give some other examples, like for the sensors that can be easily accessible, and perhaps some other examples that are not easily accessible? Sure.
So the second attack I will talk about is the sensor related ones. So this first set of attacks is focusing only on performance counters. So computational footprints, right? And later we'll see that the sensor data, of course, exposes some information, and it's not so easy to manage permissions for it. So the mitigation is not, traditional side channel mitigations don't seem to work, and I'll give some thoughts why. And permission structures require some thought. It's not an easy problem to develop, right? It's something that we need as a community to think about. So this is coming. Please excuse me for differing for a little bit.
And I have a question as well. For eye tracking, is eye tracking also not vulnerable to attacks? Because eye tracking is used for full rendering, but as well some games is trying to use eye tracking for target aiming and such things. So
so we haven't drilled so much into eye tracking. I think one of our headsets does not have it. And so I don't know the answer to that one. I think it's harder to manage permissions for eye tracking, right? Because potentially you need it for multiple applications. You don't know when when you need it. So yeah, that's a great question. I don't know the answer for that one.
No.
Okay.
Can I also have can I have a follow-up question on like my previous question?
Sure. Yeah.
So if some of the sensors can be easily accessible, like for example, the shared buffers to many applications, then does it mean that even if we have like on-sensor computing and just passing like part of the data, or say the features to the main computation unit, even we apply this way, it might not protect the privacy of the user?
Yeah, I think it depends, right? I think it's one of the promising ways to think about protection, at least for some targets, right? Because as you abstract the information away, perhaps the low-level signal that discloses information is no longer available, right? I don't know. I mean, I guess we have to try it before before we can say that, and it's really tied to your target. So if your target is like computational, then the time scale that you're talking about is, you know, nanoseconds, you know, microseconds. If it's something that is mechanical, like human gestures or something like that, then we're talking about milliseconds. So as you abstract away and reduce the resolution, you know, either by reducing the resolution directly or by kind of moving to some other representation, it depends on what your goal is, how successful that is in blocking the information leakage.
Okay,
yeah.
Thank you.
Okay, great.
So I'm gonna another question that you proceed, but so is your work mostly looking at assuming that everything's happening on the headset, or do things change when you offload things to the cloud?
We haven't looked at offloading yet. We know that that's coming in products, and that obvious. So that's maybe part of my comment about the systems not being fixed. So this is where this is still focused on everything is on the headset. We have some work, and there are some other people that have done some work on kind of spying on network traffic, for example, and that has some leakage. So as you offload, for example, that becomes a target, and you know you have to think about what's running on the headset and what's running on the server. So yeah, the problem changes, I think, when we have offloading.
Yeah. So ILLIXR now we do offload some parts. So.
Oh, okay, great. Yeah. It would be great if we can talk, you know, later about how these things apply to ILLIXR or don't, and how they would change. Yeah, thank you. So I'm just gonna give like a little bit of maybe intuition about how this leakage works. So in this case, you know, this is the hand gesture attack. So from the first class of problems, which is the interactions. And as you can see, there is a performance counter for the vertex count that is being processed. And then depending on the specific gesture, the complexity of what gets rendered is different. And then, then you see that there is a difference. So as the SPI samples and samples, there's a different signal that you see for the vertex count that kind of can help you fingerprint what is happening. Notice that the y-axis is different. So it's not just the shape, it's the intensity of the signal that changes. If we look at an example from the second category, when we're trying to spy on what other applications are running, in this case, we collect data when a user basically starts a new application. And as you can see, we are tracking the frame time in this case. And as these different applications start, so you see Microsoft Edge, OneDrive, and Mail. So they were among the most popular applications in the Microsoft Store. You see that the computational fingerprint is different based on the intensity of the computation that these applications do as they kind of get launched. Of course, you see that the time scale is in seconds, essentially. So there's a very clear fingerprint that depends on the type of application that you are launching. And this is an example from the environmental types of attacks. So here again, we're tracking the CPU frame rate, and the SPI in this case also enables this meshing of the environment where where we're asking basically the environment to be covered by these triangular meshes. So that introduces some computational overhead when the environment changes. So we see a dip in the frame rate that corresponds to the bystander. So these I think are mislabeled. So this is when they step in view, and this is when they step out of view. And what's even better is that the size of this dip correlates with essentially the viewable size of the bystander. So we can use this to estimate the distance of the bystander from the headset. And we were able, so once we ran this through a machine learning pipeline, we were able to figure out the distance down to like a 10 centimeter error range. So this is sort of the intuition or kind of an example of the signal that you can see, but in reality, there's a bunch of these performance counters that we are able to collect. And we have essentially a time series side channel signal. We run this through a time series library to do feature engineering and selection. And once we find the most salient features, we train classifiers, or in the case of, for example, estimating distance regressors, to kind of translate the collected time series into some inference about, our victim, some inference about, the secret value or the private value that we're trying to learn about the victim. And just to give a sense of what this looks like, this is the hand gesture attack, both on the HoloLens and the Meta Quest 2. And this is the set of, so essentially these libraries take a time series signal and then kind of compute some statistical features on it. And I'm not going to get into the details of those, but once we do the saliency analysis, you can see that the features themselves that are most salient were different across the two headsets. But you can see that they're related to CPU frame rate, to the GPU frame rate, to the vertex count. These were the ones that are bolded are the three most valuable features. Once we run the whole pipeline through and we run it through a classifier, we didn't use like deep learning or anything super fancy because basically collecting data is a challenge. I mean, this is manual effort to have enough users and, run the IRB protocol and collect enough samples to be able to kind of train something and then test it on some of the unseen traces. As you can see, we can obtain like an F1 score of, 92% or 90% on the two headsets, which is, as far as side channels go, very, very good performance.
So this is based on user studies or not? So you did the
this is based on user studies, yes. Yeah.
And then how many
I'm sorry, Sarita, I have to be careful. So I think our initial set of data was not based on user studies, but without IRB. And we got basically chided by the conference reviewers that we need to do that. And GIASI had an IRB protocol, but we had to file another one for this specific purpose. And the second set of data that we are collecting, because as part of the revision, they also asked us to expand the data set, is following the IRB protocol.
Okay, and so what is this actually telling us here? I'm not actually sure what.
Sorry, I'm providing examples, so maybe I'm not being complete because there's a lot of attacks. So this is the hand gesture attack where we have a choice of multiple hand gestures. Yicheng, you want to jump in and say how many?
They actually have like 5 or 6 hand gestures in the HoloLens tested.
Okay, and essentially, so then we do that feature engineering and decide what are the most salient features. We collect the time series, and this is how well we guess the gesture that happened. So the F1 score for identifying the 1 out of 6, not super impressive, but still, there's no reason to think that it wouldn't scale to other things. So we have also like keystroke identification with similar performance and so on.
And this is all based on the performance counter information.
This is based on the performance counter information. Yeah.
Interesting. And then what else is, sorry, I'm like asking too many questions.
Yeah, sure.
What else is running when you're collecting this information?
So most of our experiments were the victim and a spy. But Yicheng did some experiments to see if there is kind of interfering noise as well. And the quality of the channel degrades a little bit, but there's still a lot of signal. So it's not enough protection if there is other things that are happening.
So yeah, I guess my question really is, so I haven't really looked at what kind of counters HoloLens or Quest 2 make available directly. And so they are specific to hand gesture inference? I mean, are they
so these
how
are
do you isolate? Yeah,
these are Unity Unreal performance counters. So I assume that ILLIXR, if it's compatible with those, would be also exposing the same things. And these are the raw performance counters that we are collecting, right?
Right, but what does CPU frame rate mean? I mean, this is like the frame rate for the hand tracking component that's running, and you're able to,
Yeah, we believe it's the frame rate for the headset, right? So as it gets more computation, it's not able to render as fast. So the frame rate fluctuates with what's happening computationally on the system.
I mean, in an XR workflow, there are many different frame rates, right? There's like a bunch of stuff happening, and each one is kind of in the runtime, each one is scheduled independently and has its own frame rate, right? So head tracking its own frame rate, hand tracking works in its own frame rate, rendering works its own frame rate. So I'm just wondering what it is that you're actually monitoring here. Yeah.
So so I'm sorry, we're not. The short answer is we're not sure. This is the frame rate API that is exported by Unity Unreal. Okay. Yeah, my guess is because it's a single value that it's some global frame rate for the system, but we're not sure. Yeah, if there's final. Yeah, sorry, go ahead.
Sorry, I was just going to jump in and say, yeah, I think it includes a bunch of things, right? So it's anything that's computational. So like maybe the hand gesture tracking or recognition, or maybe like the processing of the spatial environment information. But yeah, we haven't broken it down to individual frame rates. I'm not even sure if we can get that from the Unity Unreal API. Anyway, sorry, Nael, continue.
No worries. And if we can get it, then that's additional information. I think that's additional leakage that we can exploit. Yeah. Okay, so the second kind of effort that we have in this area, it just so happened that they got done separately, and we have two papers reporting on this, was to think about essentially the API, the tracking APIs and sensors. So these are not computational, but these are, you know, the values that you are getting from the sensors most of the time. And rather than just thinking of this as another source of information, perhaps for the mechanics of the attack, it's that way. It's also different because you know, in these devices, reality is shared, so it's hard to think about how to separate those out. So this is maybe related to the discussion that we started having, you know, 10 minutes ago. You can't just say that easily that the sensors belong to this one application, because otherwise these other applications cannot track reality to be able to, for example, as you change your field of view, to change how they are displaying and so on. So it's harder to think about how to isolate this information, or how to present it to or limit its access to it to the different applications. So in this attack, we are trying to see if we can infer from the head pose information what a user is typing on a soft keyboard. So there's a soft keyboard, and the user is typing stuff. And as I mentioned, there is this HoloLogger paper out that did the tracking of that did the hand tracking. So that is like a direct correlation. As you move your hand, if you track it, you can see where it is on top of the keyboard. This one is perhaps a little bit more subtle in the sense that it's not clear that your head should be moving as a function of, or in a way that correlates with what you are typing on the keyboard, right? So this is what we tried to do. So there is a foreground application, and maybe you're typing something in it, and then the background spy is basically collecting this head tracking information and trying to infer from it what you are typing inside of the foreground application. So this is Carter doing the experiment, I guess. So is there
any intuition here that how does the head tracking affect where you're moving your hands?
So the intuition is basically, as you type, you're looking at the keyboard, right? So you change what you're looking at. So if the space bar is down, so these keyboards in AR, VR, they spread across the field of view. So it's actually quite, you know, you have to look around to find the key and so on. So there is information that is embedded in the motion of the head. Yeah. So these are some of kind of the early experiments that Carter and Giassi did to sort of see what the signal looks like. And these are three different signals from the head tracking. So there's the gyroscope data. And as you can see, there is a fairly predictable pattern that correlates with what it is that you are typing at that point. Okay. So this is the high-level overview of this attack. So we're collecting the gyroscope and accelerometer data, right? So 6 different signals. And then we're running them through a sentence segmenter that tries to identify the word boundaries. And we tried both to identify word by word, but also to identify character pairs. So moving from A to Z versus moving from A to H or something on the keyboard. And the goal of doing this character pair is potentially it can be helpful in sort of password identification, where it's not really, you can't train on words. The passwords are unpredictable and potentially unseen in your data. So if you can break it down to the character level, perhaps that can be used to also kind of infer passwords, not just what is being typed in terms of like English text. And the segmentation problem, initially we had sort of an artificial study where we had like a submit button after every word, and that kind of made the segmentation problem go away. So on the left-hand side, you see the signal as the user is done typing, goes and has that exaggerated kind of motion to go to the submit button. But eventually we were able to sort of auto-segment without that. And we conjecture that part of that is kind of the space bar is at the bottom of the keyboard. So therefore, as you move from word to word and type the space bar, there is kind of this repetitive signal that you can use to identify the boundaries between the words.
And do you have numbers for like how long all of this takes? What kind of networks are these? The reason I'm asking is you're running this background process on the headset itself, right?
Yeah, the background process to collect, but the inference happens offline, right? If you want to do it online, then it becomes different. So we run and collect data, and then later we do the inference.
Okay, yeah. So this is not a scenario where the attack is actually happening on the fly.
Yeah, so you could perhaps stream the data out on the network and do inference with a little bit of delay. We haven't kind of done this like an online where you see the text as it's being typed. Yeah.
Sorry, I have a question here.
Sure.
So for this kind of attack, how do you distinguish the contributions from head movement and gaze movement?
So we're not tracking gaze at all. So this is head movement, and it seems to generalize across. So our user study is like 10 people. Each of them did experiments multiple times. So it seems to generalize across them, although we made sure that nobody knew the purpose of the experiment, so there weren't exaggerated motions and so on. And there is variation between like, people that are animated as they type and people that are more kind of doing, gaze information, but there's still remaining signal across at least the users that we tried, right? It might be that there's somebody that, has never moves their head and it's all gaze movement, but we haven't seen it in our limited data set.
I see.
Yeah.
So also, Boyan, what they're doing is collecting directly sensor data from the gyroscope and the accelerometer, right? So it's not like, so there's no confusion here between head and eye movement, right?
Yeah. So this is directly the sensor data. It's accessible at user level on the headsets that we tried. So this is not, it requires no special permission or setup or anything so any application is able to get this information without additional permissions.
Yeah, I get that. Initially, I was just thinking about a use case that if your head is not moving and the only motion part is your eye, then how does that affect the result? But it sounds like your user study results does not show that.
Yeah, I think this is potentially a function of the also keyboard size. So if you have like a really small keyboard where you could do all of the motion without moving your head, maybe there isn't as much signal. But on the keyboard that we tested, which is I think a standard keyboard on these headsets, there was enough motion to be able to track that, right? So you wouldn't perhaps be able to span the whole keyboard comfortably with just moving your eyes.
Yeah, sure.
So hypothetically, if you were some very important person, very paranoid about security, you could stop moving your head and then only squint your eyes and type, and that would stop this attack, right?
For this source of leakage, right? But who knows about other sensors, right? So the problem is bigger than this one instance, I think, right? So yeah.
Or you would type garbage, right, as you moved your head around.
Yeah. Yeah, exaggerated.
I think what
Go ahead.
I was going to say not all headsets have eye trackers. So this attack is on the Quest 2, so it doesn't have eye tracking, right? Maybe the Meta Quest Pro, whatever it's called, it does have, but this some don't. Yeah.
So I guess what Boyan said.
Yeah, go ahead.
Sorry. So I guess what Boyan said could open up another type of attack, or even like a combination of like gaze tracker and gyroscope to make it more vulnerable for the users to, like, in cases of entering the password.
Yeah, I think so. Yeah, you could fuse multiple, the more data that you have, provided that it's not kind of redundant or correlated, the more information you have to exploit. I completely agree. Yeah.
Exactly.
So the thing about, sorry, who was talking?
Oh, I'm sorry, I interrupted you. Go ahead.
Go ahead, Mike.
You're waiting for me. Can you describe the frequency at which the data is published from the different platforms? Maybe they're different. Like it updates its frame rate or position information every 100 milliseconds.
Yeah, my understanding is it's at frame rate. So so basically that's for all of the signals that we are obtaining. Yeah. So I'll talk a little bit potentially about whether you can, if you reduce the resolution, whether that would work as a mitigation. And the short answer is it doesn't seem like that's the case, right? So for some other side channel attacks, this is perhaps a standard way to defend, basically reduce the resolution of the information. First of all, this interferes with legitimate functionality for some applications, but also it doesn't seem to be able to block these channels because, the phenomena like typing is slow enough that even if you reduce the sampling rate, there's still a signal that you are able to obtain. Yeah. Okay, and this is sort of illustrating how these signals for two specific values tend to be consistent based on typing. So this is the word lazy, and you can see the pattern that you get through the head motion tracking, and this is the word quick. So the two things to see is that vertically the patterns are consistent, and then horizontally for the different words they are different, right? So this is what we need to be able to classify effectively. So again, in our initial experiment, we had basically a 20-word corpus to try to demonstrate that we can identify which word it is. And again, this is mostly not a function of the limitation of the attack, but function of the difficulty of the data collection. And the reviewers asked us to significantly increase that. So perhaps I'll have better numbers for you next time. So if I did a random guess, you can see that top 1 accuracy would be 1 out of 20. Top 5 accuracy would be 5 out of 20. When we used the Rocket classifier, we did better than that. And when we did the convolutional neural network, then the guess was very good, right? 75% on guessing the word and 99% on having the word among the top 5 guesses. And this is on the Quest 2.
This is with training on just 10 people?
Yeah, this is the training is actually the whole set is 10 people. So the training and testing is on 10 people, and each of them repeated the experiment multiple times. But basically that's the size of
you tested though on the same set of people that you trained on, like.
I mean, so we did k-fold cross validation, so standard things. So what we test on is not what we train on, right? So yeah.
That's pretty interesting. Yeah.
Okay, so when we start to think about mitigations, I think I already mentioned all of that. So our baseline is at frame rate. So this is going back to the performance counters. If we say, okay, let's limit the access to, every, 10 samples per second, or 5 samples, or 2, or even 1 per second, and you can see that the F1 score is still meaningful. There is leakage, and with offensive work, it's you really want anything above random is considered an advantage, right? So it's not good enough that the F1 score drops to 50% or 60%. So it doesn't seem like coarsening the APIs is an effective solution. And this is for the hand gestures. So I suspect if we did this, for example, for maybe the application fingerprinting, there might be a little bit more success, even though the launch process took 2 seconds. We're looking at maybe faster phenomena over there. So it seems like we need different solutions. So whereas this is perhaps kind of valuable for traditional CPU side channel attacks and GPU side channel attacks, it doesn't seem to be, at least a game changer as far as protecting AR/VR applications. So we are kind of thinking, we're thinking in this space. We need to identify who has access to what, understand that, what is the legitimate need for information, perhaps a different, so if you're typing something on a keyboard, perhaps that's a different situation than if you're not. We need to understand what to share and when, and make informed trade-offs between functionality and security. So it doesn't seem like we can just import sort of the permission structure on Android, for example, that says you have access to this or you don't have access to this. We need to think about what permission structures look like for AR/VR, right? Both in terms of the performance counters, but also in terms of the sensors. And the same thing we observed. So this is trying to also coarsen the sampling on the attack that did the head tracking. And as you can see, so as we go from the default to kind of much lower rate, we're still like very accurate in terms of, top 1 and top 5, right? It's not, coarsening is not sufficient to prevent the leakage in this case. Yeah, thank you.
Great. Michael, you have a comment on the chat. Do you want to say something?
Yeah, I know we're out of time, but yeah, great topic. I support the idea of like continuing on another meeting and discussing more. But yeah, it makes me wonder if like we use the WebXR API, so that would be like a nice way to like turn off some of these. Like I'm in a secure state. Don't distribute any data. I mean, it could be other systems, other sensors that are happening. But I could see that being, it might be tricky to get the user experience right, but that could help.
Mm-hmm. Yeah, I agree.
Yeah, so I think it would be great to have another meeting, but we should figure out the agenda for that, right? So I think, Nael, if you would like to expand on any of this, I mean, that'd be great interest. I think there are several others who couldn't make it today, so I'm pretty sure we will have a large crowd, but I will leave it up to you as to the timing, if you want to do it soon or...
I think maybe if we do it, let's say in a couple of months, maybe, I don't know, around after the turn of the year, if possible, then we might have fleshed out some of these things a little bit better. Or I don't know. I mean, I'm also like very interested in getting more into ILLIXR and discussing possibility of exploring how these things apply or not. So I don't know if this could be a separate meeting that we discuss potential collaborations in this space.
Right.
Yeah.
Maybe we can do that offline as a separate thing.
Sure.
Just a much tighter thing. I don't know, Mike, do you guys want to have, like, do you want to lead something here with Arena and ILLIXR and things that Nael said?
Yeah, we can. Let me talk with Anthony, Nuno, and see if that's the right move. But yeah, we like this topic a lot. We're always concerned about it because we're a web-based XR technology.
Yeah. So let's so we already have something scheduled for the next round, which takes us into November already. Let's have an offline discussion, Mike, between Anthony, you, Nael, and us, and we can see what's the right way to proceed on this.
Sounds good.
Great.
Okay. Stefan, did you have any thoughts on
just that it would be great to have a second session. I think I personally have a lot of questions. I'm sure a lot of other people do. So even if even if we don't have a ton of new material, I think even with this, we can have a pretty good discussion.
Okay, why don't we just decide that right now? So I think we have something scheduled for the 9th, and then there's Thanksgiving. So December 7th is our next open slot. I don't know if that works for you, Nael. I mean, if we schedule something.
I have travel scheduled November 12th to December 5th. Yeah, I'll be a little bit jet lagged, but yeah, I think it should be fine.
Yeah, okay. Not to put you on the spot, just let me know. Let me know. Just send me an email.
Yeah, and perhaps Yassi can lead the next session, so that yeah, I'll definitely attend, but you get to hear from her perspective as well.
Sounds good.
Yeah.
And Yassi, I don't know how you feel about this. But like, you can just let us know offline, and we can figure it out.
Yeah, no, I think it's super interesting, and I definitely want to learn more about the ILLIXR side of things and see whether some of these things we're talking about today would apply there too. So I'd love to chat more.
Okay, so should we just decide on December 7th? We will continue with this.
Yeah, sure.
Okay, cool, awesome, great. Anyone else? Javier, I know you were very interested in this. So, do you have any quick thoughts?
So I would like the security guys comment on this, but I don't know if they're still on the call.
Yeah, I think we are over time.
Let me see here. I don't know if Marcio or you guys are around.
Yes.
No, I'm asking the
yeah. So Shabir dropped out. I don't know who else was there.
Maybe Marcio. Marcio was there too. Yeah, but you know, regardless, we're interested in the topic. So we would like to follow up as well on this. So definitely, there is interest from our side on learning more.
Yeah.
Great.
Okay, sounds great. Thank you so much, Jesse, Nael, and Yi Chang, and whoever else is here from Riverside. We appreciate it.
Yeah, it was a great presentation. Thank you.
Thank you very much.
Thanks.
Thank you.
Thank you, guys.
Bye. Take care.